Okay, hi everyone. We're going to get going, otherwise we're going to run out of time. It's my pleasure to introduce Sergey from UC Berkeley.
Great, thank you. All right, so it used to be that the way that AI would work is that we would, in the olden days, collect a large data set for whatever task we want to do, like segmentation or classification, and we would train a large supervised model to solve this task, and for every task we wanted, we would collect its own large data set and train its own large model. But now, of course, increasingly, the way that AI works is that we collect large amounts of unlabeled data from the web, we train a large self-supervised model, a foundation model, and then we use a much more modest amount of data to either fine-tune or prompt it. And that's really, really good, because now we can solve a whole range of tasks for which we might not have huge data sets available much more efficiently. Now, in robotics, we're kind of in that same place where we used to be before in the rest of AI, where for every robotic task, we either train a separate policy or design a separate controller, whatever that task might be. And perhaps in the future, we'll also move to a future where we would combine all the data from all the different robots, different tasks, and different environments to train a general-purpose self-supervised robotic model, which could then be efficiently adapted to whatever robotic tasks you might want. And I think this would be an excellent recipe to finally get robotic learning out of the laboratory and into the real world. So, what do we need to do to bring about this future, and what steps have we taken so far to get there? Well, there are, I think, three main components we need to figure out. The first is large-scale robot datasets. Chelsea Finn's talk earlier in the day talked a lot about this. I think we also need the right algorithms, the analog, the kinds of self-supervised methods that have been instrumental for things like language models and generative AI. What's the equivalent of that in robotics? We also need flexible and general models that can not only consume these large data sets, but also be adapted efficiently to whatever downstream tasks we might want to apply them to. So I'll give two examples of work that we've done that I think represent significant steps in this direction. The first one, which some of you might have seen out in the hallways, is the design of a general-purpose navigation model. So we're demoing it actually at this at BARS. The way that we went about this work is we first collected data from many different robots, some our own, some that we borrowed from others, depicting all sorts of navigational skills. And we trained a general-purpose navigation policy that navigates to goal images, and it does so across all of these different robots. And it can actually generalize to new robot types. For example, it can fly a drone through hallways despite never having been trained on data from drones. We can scale this up using a large-scale transformer with tens of millions of parameters. That allows us to generalize to an even wider range of morphologies, like quadrupeds. We can also adapt the model to downstream tasks. So for example, we can take the model, freeze all of the weights, retrain the goal encoder to instead represent turn-by-turn instructions, and then fine-tune this to do autonomous driving in the carless simulator, despite having pre-trained it entirely on real-world navigation. People have used this model all around the world, from Estonia to Finland to the United States, and of course it works here at BARS in crowds. I will let you in on a secret. The robot was actually not trained around people, so the fact that it navigates around crowds is pretty cool. I think it thinks you guys are all trees in a forest somewhere at Richmond Field Station. We can also combine this with offline RL and then do online RL fine-tuning. So we can pre-train with offline RL to get value functions, and that enables really rapid online RL fine-tuning with image observations. We can train in tens of minutes from raw pixels. We can train indoors and outdoors. Outdoors that acquire skills like preferring to drive on paved paths whenever feasible to accelerate better. And the fact that it learns with online RL in just tens of minutes from raw pixels I think is pretty remarkable. Usually this kind of stuff would take hours to do from scratch, but these pre-trained models enable a lot. If we want to apply the same kind of idea to manipulation, of course we need large manipulation data sets. We've made progress on this with Bridge Data v2. It's a data set with over 60,000 demonstrations with hundreds of objects and full language annotations. And just using a sufficiently diverse data set already enables existing fairly simple methods like goal condition policies to perform a huge range of tasks. So here you're seeing the same goal condition policy that is able to do sweeping, object manipulation, cloth, manipulating furniture. Here you see the same language condition policy doing a wide range of tasks. So having the right data really enables a lot. We can combine this again with offline RL. We develop methods that can allow us to pre-train value functions with offline RL from actually video data of humans as well as robot data, which gives us excellent representations, and can then fine-tune with RL to downstream tasks in tens of trials. And this works significantly better than methods that don't use RL, than methods that rely on imitation, and also works better than methods that don't use videos or methods that don't use large amounts of robot data. And of course, as Chelsea discussed in her talk, we can combine multiple datasets from multiple robots for manipulation as well. If we combine bridge data with lots of other data sources, that's what we did in the RTX project, we can get much more impressive generalization. Here, this combined dataset consists of 60 datasets from all around the world, from 34 different research labs, depicting 22 different robot embodiments, and about 527 skills. if we train a policy on all of this, that policy can control many different kinds of robots. So all the videos that you're seeing here, these are robots that are controlled by the same exact policy trained on the consolidated RTX dataset. If we actually evaluate these policies in comparison to the particular policies that each laboratory that contributed to the dataset used for their own tasks in their own lab, the resulting RTX policy most of the time does better. In fact, on average, it improves by 50% over the policies that each individual lab had for their scenario, which was a different policy in each case. So cross-robot learning really does work. It works for navigation. It can enable robotic foundation models that people can use, that other people are using right now in Finland, Estonia, Princeton, and here at BARS. And it can work for manipulation if you combine enough different sources of data. I do think there is a lot left to do. I think we have the essential set of ingredients in terms of we know what those ingredients are, but we do need to do a better job of actually building those ingredients. We need data sets that are more representative, cover more of a range of tasks. We need offline RL methods that are more scalable, and we need to study in more detail how these foundation models can actually be fine-tuned to a wider range of different behaviors in different scenarios. Thank you all for listening.
Thank you, Sergey. Any questions?
Yeah, I don't know if this is a super conceptual question, but how similar are these current tasks that are being aggregated into one data set? Are they quite similar? Are they completely different?
Yeah, that's a really good question. And of course, that is the parameter that you control if you want to make this work. So that's why actually navigation happened 2 years ago, whereas RTX happened this year. Navigation arguably has a lot more structural similarity across the different domains. So even though in the navigation domain, some of those robots are full-scale ATVs that are 5 meters long, and some of them are small RC cars that are 10 centimeters long, there's so much structural similarity that it works. For manipulation, the policy that we actually trained, that we deployed in all these settings, was all trained on data from robotic arms with parallel jaw grippers. Now, the data set also contains other stuff, but it's not used for that model. So in principle, that is kind of the next frontier, is to further grow that range of different embodiments and heterogeneity that can go into that model.
Thank you.
Thank you, Mark. Our next speaker, Mark Cutkosky from Stanford.
All right, good afternoon, everyone. Sure it would. Good afternoon, everyone. I'd like to, for a change, talk about some hardware. ReachBot is a NASA project led by Marco Pavoni and Aeroastro, and our other collaborator is Mathieu Lapotre, who is a planetary geophysicist. And the immediate motivation is to be able to go inside caves and lava tubes on Mars. These are areas of intense scientific interest. If you're a biological organism, it's maybe one of the very few places on Mars that you could survive for a while. And so there's a lot of interest, but as you can see, it's also a very formidable environment to try to negotiate. And in particular, if you want to do any kind of forceful interaction for doing science. So there are robots that climb rocky surfaces. A very nice example is Lemur from NASA Jet Propulsion Labs. But the problem is that if you're a small robot, then the world is full of large obstacles that you have to clamber over. What if you could have a small robot body, no bigger than needed, the size of maybe carry-on luggage, with really long arms? Then you could overcome some of these problems. It's a good idea. It's been around for 1 million years or so. The problem is on Earth, it doesn't scale very well. Mass goes as length cubed, and so we don't see any of these with a body the size of carry-on luggage. Unless, of course, gravity's not a problem. The other thing we have going for us, okay, gravity is less on Mars, but it's also, we have materials that nature can't use. And in particular, we're using these deployable composite space booms. These are used for antennas, other structures in space. They have a fairly high strength-weight ratio. They let you get out 10 meters and more. And that's important because when you're climbing, I don't know if any of you have ever been rock climbing or you've been to a climbing gym. If you have, you probably at one point or another wish that your arms were, a little bit longer to reach for handholds. The other thing we do is we put a gripper at the end of each arm. That also works well. There's good precedent for that. And it turns locomotion into a manipulation problem in which you manipulate yourself. So that means we get to reuse a large history of grasping and manipulation theory, force closure, and all those good things. The difference is that instead of having fingers that can push but not pull, we have booms that, to a first approximation, can pull but not push because they have a low buckling strength. The one thing that's really different is the constraints. We don't have Coulomb friction and Coulomb, friction cones and that stuff. What we have are grippers now that are grasping a rocky surface. But we can model that. We've done work on modeling spines on rocky surfaces. You assume some stochastic distribution of angles depending on the roughness of the surface, and you can predict how much force you can apply in different directions. You bundle that into a grasp matrix, and now you can predict how much pull force you can take for a given grip force. And so here's some work with Tony Chen and Carlo Bosio, who's now at Berkeley, in which what they've done is a Monte Carlo simulation. What you're looking at is a limit surface. So these are the maximum predicted forces in X, Y, and Z directions at the gripper. And as you can see, not surprisingly, they get higher if your grasp force is higher. And they also get higher if you have more spines, although there's diminishing returns. You can see here that 50 spines is really not much better than 40, and there's some interesting reasons for that. The next step, and I won't say a lot about this because Stephanie Nudik has been talking about this at the poster session, is to do motion planning. So you start by choosing grasp sites, and then you have to plan a trajectory that satisfies constraints on the grasps, on the booms, on joint angles, and so on. And you move grippers one at a time, continuously controlling the tension in the booms so that you can move the body around as she did in that slide. So where are we now? What happened is I want to talk about one more thing first, which is perception. We're using depth camera, LiDAR, stereo because we want to identify good grasp sites. And the reason why that's important is that we're banking on the fact that if you have a gently convex surface at the length scale of the gripper, you can pull much harder for a given grasp force. So identifying good grasp sites is important, and this is the work mainly of Julia D. So what happened last spring is that Julia and Tony and Stephanie went to the Mojave Desert. They went inside a lava tube, and while this video plays, I want to talk about some of the takeaways from the tests that they did there. So they had one ReachBot arm mounted on a tripod. So one of the first things you see, you can even see it right now, is that grasping with ReachBot involves a considerable commitment. It's not like a robot grasping things on a tabletop, and if something falls, it's not that big a deal, or it's easy to plan a new grasp if one didn't work. It's almost like perching. By the time you've got something out 10 meters or so, you want to be pretty sure that it's going to be a good grasp because retracting, re-aiming, repositioning is time-consuming. The second thing which is showing up right now in the video is that we're doing a two-scale approach to sensing because with sensors in the body, you want to say, that looks like a good place to extend an arm out to it. But then as you get much closer, you can pick up much more detail about the roughness and about the local geometry. And finally, robustness is important. I mentioned that the spine behavior is stochastic, and even if the spines don't ever slip, the rock itself could fracture. So you want to plan poses that are robust with respect to these rare but unavoidable failures. And so with that, I know I'm out of time. Let me close and take any questions.
Any questions? So if I may, Mark, and if I can encourage you to maybe use this to answer. Sure. How do you power these things? How power intensive is this mode of locomotion?
It's neither more nor less energy intensive than any other kind of locomotion. It's slow, so we're not talking about dynamic loads. And your main sources of energy dissipation basically occur at the gripper. So, yeah.
Thank you very much.
Yeah, Ken.
Have you thought about using it during as compression as well?
You can do gentle compression, but and you can do it more if the booms aren't extended very much, which means if you want to work on something locally, that's definitely an option. When you're 10 meters out, you can't really do very much compression. Yes.
Yeah, hi. Are you using, so you're using touch and vision and for navigation?
Vision mainly, yeah.
Vision mainly. I was going to ask, so is touch, how important is that? Is there work to be done there to improve?
You need to know what forces you're applying at the gripper and on the boom. what we're not doing right now is using any kind of tactile sensing at the gripper to determine, how reliable the grasp is likely to be before we start to pull on it.
Okay, thank you very much.
Yeah, sure.
Our next speaker, Jeannette Bohg from Stanford.
Hello, everyone. So thank you, first of all, for all the speakers who have given great talks and to all the student talks. And I think there's many works out there that try to learn a robot manipulation policy. And they often only use RGB images. And I'm really wondering if this is all there is as input. And I think many speakers have also talked about vision and touch. And I think this talk is actually going to mesh very well with what Jitendra also talked about. So I often wonder why humans are so good at this manipulation task. I think there are many answers to this, like how this, or we humans with our 20-watt brain can solve tasks like this. Even like this kid will find out soon that this is not a good block to pull from this tower, but probably learn afterwards to not do this again. So I think we need some better algorithms to learn from trials like this in a very fast way. But another point I want to make is that humans also use more than just their visual sense. And robots could do so too to solve manipulation tasks. So robots often have cameras, of course, but also audio sensors, tactile sensors, force torque sensors, joint torque sensors. And I'm really wondering how we can combine all this information to do better manipulation. And like quite a while ago now, in 2018, we really asked ourselves this question, like how can we leverage this complementary sense of vision and touch for context-rich manipulation tasks like this insertion task that we used here as an example, where these different sensor modalities really have a very distinct signature. And we basically used this kind of structure to look into this problem where we learned an encoder that would produce a state as input to a policy to then output end effector displacements. And we specifically used a self-supervised representation learning technique that could fuse all these different sensor modalities without actually requiring any manual labors. And so we were able to do things like this, where my student Mykel here perturbs the robot and can still insert. And we really wondered like how important is actually each modality. So this was a follow-up work where we also added depths to the problem. And here's a chart that we made based on this work that's very similar to what Jitendra has shown in his work, where you can see on the left side what happens to the success rate of this robot inserting pegs when using all the modalities. And then you can see if we take out depth, for example, the success rate really drops by a lot. And so I think that's like another data point for you to, maybe to ask the question, like how can we use all these different modalities that we actually have available on a robot? So I think one answer to this question of why humans are so good at this is that the sense of touch and depth understanding actually really helps. And another hypothesis could be like to actually use more object-centric representations and whether this could actually help to improve generalization over learning a latent vector from a full RGB image. And so with this, I want to tell you a little bit about this new work that just came out on Archive about Sim3 equivariant visual-motor policies beyond rigid object manipulation. And so the idea here is that we want our robots to be able to do what humans do, which is give them a few examples of how to solve a manipulation task, to then really generalize to, the same manipulation task, but with different rotation scales and other problems. We asked the question, like, how can a robot learn a visual-motor policy that can take example trajectories from a single source manipulation scenario as input and then generalize zero-shot to scenarios with unseen object visual appearances, scales, and poses. And so we proposed this architecture that we call EquiVact, which uses Sim3 equivariant network structures that guarantee generalization across all possible object translations, 3D rotations, and scales by constructions. And thereby these network structures can also allow generalization of the robot policies. And so this method consists of two phases. And the first way is we pre-train a SIM3 equivariant visual representation on simulated scene point clouds. And in the second phase of this method, we learn a SIM3 equivariant visuomotor policy on top of this representation using only a small amount of source task demonstrations. And so now we want to show how this works on robots. Our real robot setup consists of 2 Z cameras for getting point clouds of the scene, and 2 mobile bases who you met already this a bit earlier. This is basically 2 tidybots. And we want them to basically manipulate this target object. So we test our method in these 3 manipulation tasks of close folding, object covering, and box closing. And here's a source demo and what the robots can do. And this is kind of the variations that we had. And because I'm out of time, I'm gonna show you just a few more demonstrations where we show like how from this tiny source demo done by a human, we can really generalize to these 2 robots doing the same task on objects that have a very different object aspect ratio, for example. So if you're interested, check out this website. And so to answer this question, I think two answers are you should use the sense of touch and depth to improve sensory motor control. And I think these object-centric representations really help generalization. So thank you very much for your attention.
Here we go. So first of all, thank you to all of you for sticking around for the afternoon session. I think I've been abandoned by my own collaborators and students, so I very much appreciate you. So second order of business is that I have a confession to make. I am not a roboticist. I am an interloper in your midst. So instead, my research is broadly in the area of wireless communication and sensing, with a particular focus on enabling sustainable technologies, including agriculture. That said, I do collaborate with roboticists, including Steve McGuire, who you heard talk earlier. So for my talk, I'm going to cover something a little bit different. I'm going to take a quick delve into RF backscatter and microbes and look at what role they could play in autonomous outdoor sensing systems. So how many of you are familiar with RF backscatter? Great. So it turns out all matter of RF reflects some portion of incident RF. This backscattering phenomenon is the principle behind radars and LiDARs, which we heard a lot about today. It can also be used to implement communication, though. So it turns out that antennas are very effective at re-radiating incident RF, and if you change the impedance of the antenna, you can change the nature of the reflected RF. So this allows us to implement a communications link using backscatter. The simplest systems implement on-off keying by grounding the antenna, which toggles it between maximum and minimum reflection modes, so zeros and ones. So modern systems are typically broken into 3 components. You have a transmitter that sends this incident RF. It's known as an excitation signal, a backscatter tag to reflect the RF and modulate data, and a receiver that receives the backscattered signal and decodes the tag's data. Some systems combine the transmitter and receiver into one device, which is the case with RFID, which is probably the most well-known example of backscatter communication. So using backscatter to sense soil moisture involves pairing inexpensive backscatter tags with a centralized reader that acts as a mobile edge device. And the key to how this system works is that RF travels more slowly through wet soil than dry. So by measuring how long it takes for the radar signal to reflect from the tag, we can estimate soil moisture. As you can see, this is where the robots come in. You've got a UAV right there. So anyway, pulling these things together, if you know the depth that a tag is buried at, a radar-based reader can measure the time of flight that it takes to reach the tag. The radar also measures the time that it takes to reach the ground surface, and then using some simple algebra, you can measure how long it took the wave to propagate d sub s in the soil. And finally, the travel time of the RF in the soil gives us the permittivity, which in turn allows us to use standard models for soil moisture from the literature in the soil science community. It turns out that this approach was able to achieve comparable accuracy to state-of-the-art commercial soil sensors. However, one of the nagging limitations that I want to mention right now is power and retrievability. Even though this technique has a pretty long projected battery lifetime, years, it's still a finite lifetime. And what about of the materials in the battery and the components, like printed circuit boards and chips? These go in the ground. Inevitably, some of these get lost or fail, especially if the battery dies. So what is the impact of having this technology slowly degrade in the soil? So I was mulling over this challenge one afternoon when somebody asked me, have you ever heard of dirt batteries? No, I had not at that time. So dirt batteries are more formally known as microbial fuel cells, soil microbial fuel cells. They leverage the behavior of a specific type of naturally occurring bacteria in the soil known as exoelectrogens. These microbes produce a spare external electron as a byproduct of their natural respiration activities. This is where the name exoelectrogen comes from. And if you place an electron acceptor in the soil, in this case the anode, and place a load between that and the cathode, you can harvest energy. Fairly minuscule amounts of energy, on the order of microwatts. But electronics recently have progressed enough such that today that's actually enough to power really low power workloads, such as the backscatter chips I was just talking about. So these MFCs are not a new technology. They're fairly well known in the civil engineering and biology communities, but they're a pretty new topic for the EE and sensing communities. So to date, there's relatively little work researching the feasibility of using these as a power source in outdoor sensing networks. So some of our early experiments suggest that these cells could potentially produce enough power to sustain low power microcontrollers using backscatter for communication. So with this in mind, my vision is that we can start to transition away from traditional sensing paradigms towards a more mobile and microbe-friendly paradigm, making sensing more sustainable and accessible. And I'm just going to highlight one particular research challenge as I close. I suggested using a UAV, attaching one as making the mobile reader. But as I'm sure you're all well aware, drones are easier said than done. Even if you overcome regulatory and cost challenges, there's still the very real issue of limited payloads and battery lifetimes. So consider the fact that the average US farm is 445 acres. And then looking at the average drone battery lifetime, at least the kind that we've been working with a modest payload, it's 20 to 45 minutes. So this means that realistically, you can only cover a small portion of a farm with a given flight lifetime. So one of the questions that my collaborator and our students are trying to answer is, given limited battery lifetimes, how can you maximize the information density of your flight path? And so this line of work is one of the topics I'm collaborating on with Steve McGuire. And I'm going to skip that last one, even though it's super cool. And with that, I say that this tale of two electrodes is to be continued. So thank you all for letting me take kind of this divergent topic and talk to you about it. And if you have any questions, I can take a couple now.
Thank you. Much like the robots in Star Trek, the Bohg, we will assimilate you. And you are now a roboticist. Any questions? I have maybe a question, if I may. RFID tags, of course, are unpowered and powered through the radio. Is that possible with these, or is that just not enough power?
It's not that it's not enough power, it's more that soil is very different than air. So when you have this harvesting, you kind of have to split your budget. Some of the budget goes towards powering up the chip that does the encoding of the information, and the other part of it goes into the antenna and is reflected back. So every amount that you try to harvest goes away from the SNR of the communication link. SNR underground is like a super low power or super low SNR regime. So you really can't afford that budget, so that's why we add the external power.
Perfect. Thank you very much. Next up, we have Jiajun Wu.
From Stanford. Oh, hopefully it works.
Okay. Yeah, sorry.
Hopefully. Let's see. Okay, great. Thanks for having me here. I assume the sound also works, because this is very important as shown in the title. Okay, yeah, so I'm going to talk about modeling object sound for robotics, but actually really maybe it's by robots, but hopefully in the future it'll be more like for robots. So let's just look into or think about what happens when you hear an object sound. So here's a bunny, and assuming this is the sound of a bunny. Okay, maybe it's not, but assuming it is. So let's think about what's really going on. Fundamentally, there are a few things that really matters. One is the object actually vibrates, right? So the way that it makes sound is because it vibrates at different frequency modes. And then there's the sound field. The sound has to propagate, right? If I'm standing here, if I'm turning back, if I'm moving away, the sound I'm going to hear is going to be different. And finally, it's affected by the environment. That's why you have to spend a lot of money to build those nice like lecture halls or symphony halls because they sound well. So we have been doing projects to try to really understand and modeling all these effects and using robots in different ways. So the first one is actually collaboration with Jeannette. That's about 2 years ago. That how can we, if we look at object intrinsics, like what objects are making sound because they vibrate at different frequency modes, and it turned out you can have very good approximation of the sound they make by aggregating the vibrations at different modes. But also on top of frequency, you consider the damping coefficient for each mode as well as the gains like magnitude. And the whole process is like going from these physical properties to the object, like the vibration modes, to the sound they make can actually be made differentiable. So this is the main idea behind the work 2 years ago called diff impact. So you go from these physical properties to differentially simulate the sound of objects. And once you can do that, what will happen is now if you hear the sound, you can actually, now you know how it's actually produced, right? So it's a combination of impact forces, combined with convoluted with the impulse responsive objects. So you can actually use that to synthesize the waveform and compute what will be the sound be like. And you can compare the sound you have with the sound you actually observe and get it, based on the loss you have, you can actually optimize and search for what are the impulses, when are they happening, and what are the impulse responses to objects. So that really optimize the approximate sound you have heard. And this will allow you to, let's say, if you hear there are collisions between two objects, like a robot is hitting a cup, then based on the sound you have heard, like this, you will be able to separate the sound, right? Do source separation. The sound that you're hearing is actually a combination of the sound of a fork and a mug. So you can separate the sound of a fork and the sound of the mug. Okay, so this is a very short thing, and it's really done by a PhD student called Sam Clark. And he started as a roboticist, but then he suddenly got very into sound, and he's like, okay, can we do it more seriously? So now we say, okay, let's move on to collect sound into this anechoic room, right, which doesn't really have reverberation. You can see we can have an impact hammer to hit objects and have a microphone to record the sound the object is making. And you want to do it more systematically because now you no longer want to study the vibration modes of object, you also want to study the sound fields, how the sound is propagating. So he moved on, and instead of hitting objects with hand, we can have a robotic system that have an object that with a fixed ring match, so you can like hang in the air, with a striking mechanism. So there's an impact hammer and a motor system and electromagnet, so they can automatically hit the object. And you have a microphone gantry, so which is with the impact hammer, you have an object, you have 15 microphones, and because it's a gantry, it can sort of move. So what's going to happen is this hammer is going to keep hitting the object with the motor. The gantry is going to move and record the sound the object makes, and again, and the gantry can rotate, right? So you can actually really record the sound fields of the object while the object is hitting the middle and making the sound. He may show one, like a shorter version of this in the spotlight talk, but I thought this is really interesting. Okay, so what you get is for an object like this, you actually really have the sound field of the object, and they actually sound slightly differently. So really, this is the Sam I mentioned, and together with Rohan Gao, who was my postdoc. Okay, so just a little bit of sampling a sound field. It's kind of subtle, but you can actually hear there's a slight difference between the object and the sound they make, in particular in terms of magnitude. And you can use that. What can this be used for? At least you can use that to. There are so many work on like simulating vision rendering, as John Byron said. But there's relatively little work on simulating sound because it doesn't work that well. So you can at least use that to, for example, benchmark how the sound simulation works. So here, for example, is the real sound we collected, and the denoised version. And you can use that to benchmark how the sound simulation algorithm works from graphics and from computer vision. This is one of them. This is the second one. There's a third one. All right, so okay, I think we're getting better. The third one's from ours, by the way. Still, there's a long way to go, right? So how can we really get better? Okay, so that's the second work. And finally, I want to show the third thing. That is, we have the object that is making sound, and sound propagates. Finally, we also want to understand the sound will be different, based on room impulse responses. Again, there's no data set like that. So we have built a data set with 5,000 room impulse responses, with 2,000 music recordings in different rooms. And then there are 3 different types of room, like anechoic room, a living room, and a conference room. Again, done by Sam and a very good PhD student, Mason. And here's the demo of what this data set enables you. That is, okay, actually, I want to just hear the different room impulse responses. And actually for each of them, we also try to collect the data with people there or without the people. And we not only collect the room impulse responses, but also collect how the music that could sound in these different room environments. And finally, what this data can allow you to do is you can play the music without the human is there. This is what it's going to hear like. And you can hear the music again when the person is there. It is really similar, but maybe surprising to you that there's subtle differences between the music you just heard, and if you send it to an AI algorithm or a sensing system, it was able to tell with a 98% accuracy that whether there's a human actually in the room or not. And it can also do reasonably well in localizing the human. There's a kind of subtle signals you can tell from sound. Okay, I should wrap up. So talk about different ways that we can model in sound. There are object vibration modes, sound fields, and environments. And we use robots in different ways to try to help us to collect data. And hopefully in the future, all these different types of data sets will be also really useful for robot sensing and navigation systems. Thank you.
Thank you. Any questions?
I'm curious if you can use like online video sources like YouTube or something to add to your data set, or does it have to be super like calibrated and like
Yeah, that's a good point. As for the very first project, initiated by Jeannette get all the credit. There's a lot of exploration and actually inspired by those online YouTube videos, because people have recorded YouTube videos, not like in the wild YouTube videos, but like YouTube videos where people trying to make sound, and with especially like binaural, that you hear different things on stereo sound, like left ear and right ear. So is that possible for you to also disentangle that? And we also have the results on some YouTube videos, like people like hitting objects with a microphone next to it. So it does sort of, you can test on those things, but there's a big difference between those kind of object-centric modeling or fixed-based modeling from any type of YouTube video you see on the web, because a lot of them, the sound you hear are like ambient sound. So it's like, you take a picture of the street and there's like car moving around and those kind of things. So it's not really about the objects or the physics. So that's the gap. But for the things that are physics-based, we can actually try to do some of them on YouTube videos as well.
Great. Thank you.
Very cool. Excellent. Thank you. Steve Collins, you're set up. Thank you.
Thanks, Mark. All right. So today I'd like to talk a little bit about how we make our robots move. And mostly we use electric motors because they're versatile and robust and reliable. But they do have one key flaw in mobile robotics applications, which is that for many of the kinds of movements that our mobile robots engage in, they're not very efficient. Electric motors waste a lot of energy to produce a static torque or to absorb and generate equal amounts of work, which in theory has no energy cost. Now, springs, on the other hand, are very efficient. They dissipate almost no energy to absorb and return work or to produce a torque all day, but they cannot convert electrical energy into mechanical work. So for a long time, robot designers like myself have been trying to combine these two elements to get an actuator that has the strengths of each. And the problem has been in controlling the contributions of the spring to torque of the system. So we can build a specialized mechanism to make the spring do almost anything we want for one task, but then when we choose to switch to a new task, the spring often gets in the way. Or we can try to adjust the spring using clutches and motors, but the energy used by those adjustment elements has outweighed the savings for our main drive motors in most cases. So we recently developed a new kind of clutch that can help us with this problem. So this is a clutch based on electrostatic adhesion. We call it an electroadhesive clutch. And because the electrical energy is used statically, it consumes a tiny amount of energy compared to, say, electromagnetic clutches, about several hundred times less energy per unit holding force. And for similar reasons, it is tens of times lower mass and volume per unit holding force. And what's cool about this is that you can have many clutches in a single system without having something that's too bulky or energy hungry. And it turns out that this can help us solve the problem of controlling the parallel springs in our actuator. So here's the big idea. We've got a spring here, an elastomer, that yellow element, that's connected to two clutches. And when we want the spring to provide a torque or perform work on the output, we connect one of the clutches. When we want the spring to get out of the way, we connect another clutch that locks it to the frame of the device and then disconnect the output clutch. And then the output can move freely without the spring interfering. And notice that the spring has not lost its energy. It's locked in place. It's still stored so that we can re-engage it later to capture that energy and produce a torque. So with this approach, we can quickly turn our clutches on and off for almost no energy cost. But of course, what we really want to do is to be able to control the torque produced by these parallel springs. So one way to do that is to have several of them in parallel with the motor. And then we can choose how much torque we get from our springs by choosing which of these to engage at a given time. So now we can both control the torque of our springs and do that with low energy cost. So it all sounds fine in theory, but does it work? Well, we designed a prototype and put it through a battery of tests of performance to characterize the system. And here we've got there's an electric motor that's in parallel with the joint, and you can sort of see the clutches and springs up in the body of the upper part of the arm. And we found that, first we tested how responsive it could be, and we found that we could turn the spring on and off with about 50 milliseconds. We had closed loop response of about 12 hertz, which is appropriate for most of the mobile robotic tasks of this scale. And we can adjust the spring torque as we expected. We then applied the actuator to a set of tasks that are hard for existing actuators to perform efficiently. For example, oscillating an element with at different frequencies with different inertias, rapidly accelerating load, lifting and replacing a load, and intermittently contacting a surface and producing a high force. And for each of these tasks, we first performed an offline optimization of spring engagements using a mixed integer quadratic program approach, and then we used online feedback control to adjust the spring engagements. And what we found is that we could, in fact, achieve much lower energy consumption than with just an electric motor. We reduced energy costs by between 50% and 97%, which is almost all the percents. So that's pretty good. And we think this is compelling evidence that this approach to actuation could dramatically reduce energy consumption in many mobile robotics applications. Now, there are still some problems. That system was integrated into the robot arm, and it was kind of large. So we have ideas for creating a modular and compact version using these new rotary clutches that are available from eStat Actuation, which is a company that spun out of our lab a few years ago. And we have ideas for requiring less planning for the control to still get near optimal, energy optimal solutions. But my hope is that actuators like this will someday, maybe soon, allow mobile and wearable robots to run for far longer on a single battery charge, or to enable systems that have much smaller motors and batteries without a loss of performance. All this work was led by Eris Krimsky, who's a PhD student in our laboratory who just defended and is here in the audience somewhere. Oh, right over there. Okay. So, thank you.
Very, very cool. Any questions? Frank?
5 years of work in 5 minutes. That's the rule up here.
Can you repurpose to measure force as well, or with these? Yeah.
Yes, the actuator does measure the spring force and displacement with strain gauges and encoders. I know we're running a little bit behind, so if you have further questions, please come up and chat with us.
Thank you very much,
Thanks.
Steve. And our last speaker of the day, Mykel Kochenderfer. Mykel.
There we go. So I'll tell you about some of the work that's going on in our lab. The first project that I'll talk about relates to the Viper mission, which is launching in 2024, next year. The idea of this is to find water ice on the moon. So what we have to do is control this rover that's equipped with a radar sensor, a drill, a mass spectrometer, and so forth. This is in collaboration with NASA Ames down the street with one of my former PhD students, Edward Balaban, who's a civil servant, and my current PhD student, Joshua Ott. So there's a plan to traverse the moon, and of course it's going to react to the experimental evidence as it collects this data. And it starts out with a prior of where ice might be, but it's going to react to that. So what's involved here is, of course, modeling this as a large POMDP. And in order to capture our uncertainty in the environment, we're using Gaussian processes. And we've explored a wide variety of different kinds of approaches to planning these very large-scale POMDPs, ranging from belief state planning methods like Monte Carlo tree search and so forth. And we've also looked at other methods like ergodic control. It turns out that there's a lot of value in belief state planning. Josh has also been leading a collaboration with NASA JPL on exploration of underground tunnels. This started out as a collaboration in the context of the DARPA Subterranean Challenge. So in this work, what you want to do is have robots explore as much as possible, maximize coverage. And this involves carefully balancing global exploration with planning in the local context. And you also have to take into account uncertainty in traversability within the scene. Another project is being led by Dylan Asmar on human-robot collaborative decision-making. So the idea here is to take input from a user on what action to take and use that information to actually inform the belief update. So for an example, on the bottom left here, you can see some alpha vectors related to a partially observable Markov decision process. And the alpha vectors are labeled with the different optimal actions. So maybe our current belief state is B prime, labeled on the horizontal axis there. But the human expert might suggest taking action 1, which would indicate to the robot that maybe our belief should really be in those two areas indicated by A1. So we might be tempted to just adjust our belief point to be within that region, within that red region. But it turns out that not all humans are perfectly rational. And so Dylan has been exploring a variety of kinds of techniques to take into account the suboptimality of real humans, but still improve the belief state update. So another line of work has studied large-scale multi-robot assembly planning. This was initiated by Kyle Brown, who really enjoys playing with Legos, and continued by Dylan Asmar, who was a F-22 Raptor fighter jet pilot. We have a variety of skill sets in our lab. So Dylan saw the F-35 production line, and what amazed him was how complicated it was and how customized it was to building that particular aircraft. And so what they wanted to study was how do you produce a more flexible production line. So you want to be able to answer questions like where would each subassembly be built, what robots should collect and deliver payloads, how do we avoid collisions, and so forth. And so this required a number of different kinds of innovations. One innovation was in the task allocation and team forming component. which involves a greedy approximation that is then fed into a mixed integer linear program for fine tuning. And eventually they were able to build the Saturn V Lego set. And if you're interested in playing with Legos in a nice Julia framework, you can go to this, this URL. We've also released a data set for those of you who are interested in aviation and computer vision. This was just released. And finally, I'd like to announce that we're working on a new book titled Algorithms for Validation. This will be co-authored by Anthony Corso, Robert Moss, and Sydney Katz, 2 postdocs and a current PhD student. So building robots is really hard, but validating their safety and building trust that it will operate properly when deployed in the real world, that's also a really hard problem. And you can register your interest in getting a preview of this book, and we look forward to sharing that with you.
I swear Mykel writes more books than I write papers. Any questions for Mykel? If not, let's thank all our speakers in this last section again. So just one last quick housekeeping announcement before I give Chelsea the microphone. If you're driving, if you need to head back to Berkeley, I've got some seats in my car, so come find me quickly afterwards.
Awesome, that's a wrap. I wanted to send a big thank you first to all of you for participating in today's event and engaging with all the posters, all the research. This really wouldn't have happened with all of you. Also, a really big thank you to Brian Habakos, who did a lot of the behind-the-scenes work in terms of the catering, the food, the poster stands, and registration, and so forth. So a really huge thank you to them, or to him. Thank you also to the volunteers who helped keep our speakers on time. Thank you to the volunteers who set up and took down the posters, and also to all of our sponsors who helped pay for the venue, pay for the food, pay for the badges, the janitorial, and the AV, and the streaming, and everything. So yeah, another big thank you to all of those people.
Let's thank the organizers, Chelsea and Mark.
Yeah, and safe travels home, everyone.